Turning now to the top of page 4 in our first unit, which again is the longest unit, so bear with it. The rest of the units are 2 or 3 pages max. Okay, a liquid turning to a gas can be either evaporation or boiling. One word that covers both of these processes is vaporization. In the case of evaporation, the reason why you don't see bubbles as compared to boiling, where you see bubbles, is because in the case of the evaporation, the molecules are turning from a liquid to a gas only at the surface. Evaporation is a surface phenomenon. And so these Mickey Mouse things are supposed to be water molecules. I'm showing you the ones that reach the surface are the ones that turn into a gas. Now in the case of boiling, the boiling part of the liquid, you have the liquid turning to a gas throughout the liquid, and that's why you see bubbles. Alright, so the big difference is in one case you see bubbles, the other case you don't, which is the obvious difference. Now, as far as evaporation is concerned, if you want to change the rate of evaporation, and remember, rate is how fast, not how much evaporates. The rate of evaporation depends on 2 things: the type of liquid and the temperature of the liquid. As far as the type of liquid is concerned, if you compare the rate of evaporation of alcohol to water, the alcohol is going to be faster. Because it turns out the alcohol has weaker attractions between its molecules. And we'll talk more about that later. And then, if you're talking about the temperature of the liquid, if you have the same liquid at different temperatures, the one at a higher temperature will evaporate faster. So let's write that. The higher the temperature, the faster the rate of evaporation. Of course, the opposite is true too. The lower the temperature, the slower the rate of evaporation. The important point to note here is that the rate of evaporation does not depend on the mass of liquid or the volume or amount of liquid, because rate is how fast, not how much. Right, and focusing on boiling, let's talk about those bubbles that form. Because understanding under which conditions a liquid boils is an important point. So let's go to that. When those bubbles form under normal conditions or standard pressure, meaning at 101.3 kPas, which occurs at sea level, so I just gave you a lot of words, and an elevation of sea level, and the pressure inside those bubbles is 101.3. Or in other words, at the boiling point, at the temperature at which a liquid boils, the vapor pressure, the pressure inside those bubbles, must equal to the pressure that's pressing down on the surface of the liquid, or P surface. So this represents the pressure inside that bubble, the P vapor. The vapor pressure of the liquid. And if the surface pressure, or the P atmosphere, is another way of saying that, the pressure of the atmosphere is 101.3 kPas, then that liquid will not boil until it could generate a pressure of 101.3 kPas inside those bubbles. As a friend of mine says, at the boiling point, it's corny, but it helps, Mr. Bubble lives. Before the boiling point, Mr. Bubble is crushed. Again, the normal boiling point of water is 100 degrees Celsius. Why is that? Because at this temperature, the vapor pressure of water is 101.3 kPas. So the normal here has nothing to do with psychology. The normal here has to do with what is the pressure acting on the surface of the liquid. Why don't you turn to Table H? So you see what I'm talking about. Table H has the vapor pressure curves of 4 liquids, but we're just going to focus on water for now. See how that table works. So here you have P vapor, P vap, and here you have temperature. Let's just isolate water. If you follow that dashed line, which is the 101.3 pressure line, 101.3 kPas, kilopascals, the unit in which pressure is measured, when it intersects the water curve, drop a line down, and you'll see that comes out to be 100 degrees Celsius, the normal boiling point of water. Of course, if you change the atmospheric pressure by changing altitude, instead of being at sea level, let's say you're up in the mountains or down in the valley, then you're going to change the boiling point. So why don't we do one of those? Why don't you find what the boiling point of water will be when the vapor pressure is lowered to, let's say, 50 kPas. Now remember, when you look at table H, important point to note, you're making estimates with these curves in table H. Remember that along the y-axis, each of these boxes are worth 10. Along the x-axis, where temperature is measured, each of these boxes are worth 5. So be careful of that. A lot of students make mistakes. Okay, so you're going at 50 kPas. Let's walk you through that again. Let me erase this here. You're going at 50 kPas. Again, just focusing on water for now. Go to 50 kPas, let's say up in the mountains or something like that, really up in the mountains. Intersect water's curve, drop a line down. See what temperature you get. And it's about 80 or so degrees. I wrote it as 83 degrees Celsius, but on a multiple choice, 80 would be the correct answer. And so what we have here is an abnormal boiling point, because we have an abnormal pressure. So again, atmospheric pressure varies with altitude, with your elevation off the surface of the earth. So if you increase the altitude, like in the mountains, you probably know there's less air in the mountains, which means there's less atmospheric pressure. If there's less pressure pushing down on the surface of the liquid, then the boiling point of the water will be lower. So these are directly related. That's good to know. Again, in the opposite, if you're down in the valley where there's more air pressure, the boiling point will be elevated, will be higher. And now, let's look at all 4 liquids in table H to understand why different liquids have different boiling points. I have here the extremes in that table. And this one represents your propanone, which is commonly known as acetone, which is nail polish remover. On the other extreme, we have ethanoic acid, which is what you'd find in vinegar. And here's your 101.3 line. Let's practice getting the normal boiling points of each of these liquids. Again, trace it, intersect the curve, drop a line down. And you should get about 55 degrees Celsius for the normal boiling point of propanone. For the ethanoic acid, you should get a temperature of about 117 degrees Celsius. So different liquid, different boiling points. The question is why, though? It has to do with the strengths of the intermolecular attractions. Inter means between. See, there are forces of attraction that hold the molecules to each other, and the strengths of those forces will affect the boiling point of the liquid. So, let's think of it this way. Say you have a puddle of each liquid. Let's say we could visualize those molecules in the propanol. Letters P would represent that. And the dashed lines would represent the attractions between those molecules. In the case of ethanoic acid, the molecules are going to be closer together. The reason for that is because there are stronger attractions between those molecules. And so it's going to take more energy to separate the ethanoic acid molecules from each other, to form, therefore, a vapor from that liquid, to generate a vapor pressure, which will act against the atmospheric pressure that's pressing down on the liquid. Or simply put, the liquid with the stronger attractions is going to have the higher boiling point. The liquid with the weaker attractions will have a lower boiling point. And you'll see that relationship there at the bottom of the page. Why don't you try filling it in, and let's go with the weaker intermolecular attractions. See how you do with that. Okay. IMAs, intermolecular attractions, or intermolecular forces of attractions. Let's go with weaker on this one. As in the case of the extreme with propanol. So the liquid that has the weaker intermolecular attractions will have the faster or slower rate of evaporation. You guessed it, should be faster. Because the molecules are not holding on to each other as tightly. Again, picture the molecules in the case of ethanoic acid. My hands represent those molecules that are very tightly held to each other. In the case of the propanone, they're weakly held onto each other, so they could separate easily and turn into a gas. Therefore generate a greater vapor pressure at any temperature compared to the ethanoic acid. If it can generate a greater vapor pressure, as you saw before, it's going to have a lower boiling point. Now this is a confusing relationship here. I would circle the extremes though, to remember it. Weaker IMAs, weaker intermolecular attractions, lower boiling point. Faster rate of evaporation, higher vapor pressure. All right, one more page to go. You're doing good. I'll see you there.